Hello, in this episode, we are going to see how to implement Frozen for reinforcement learning using the DQN network. So again, this is the Frozen game. You have a starting point here and you want to step the frozen tiles to reach the goal. Can we write a program that does it? Okay. So, and it's a reinforcement learning principle. It's like getting a situation, choose an action, and then the environment will give you the reward and the next tile. And you keep playing this game and update your value function. Unlike the tile method, here what we do is that we have input, the state, and then have a neural network. So there are a bunch of neural networks here. And then output is like 4 nodes, and these are the Q values of each action choices of the given state. So, and this is a one-hot coding. So in the beginning, it's tile 1. The tile S0, then this is 1 and the other ones are 0. If you move to the next tile, then 0, 1, 0, 0, 0, 0, something like that. And here are the Q values for it. The backpropagation, what we do is that when we correct the error is that you copy the old tile, the Q values here, but replace one of them, the one that you chose the action you end up being, you do replace it with R plus gamma maximum of Q. Okay. So then what it will do is that it will do a supervised learning. So it measures the error of this old Q value and this Q value, and the error will be back propagated to adjust the weight. And this is how the reinforcement learning takes place. So let's see how we do it in the program. So here the library, we use TensorFlow Keras library to build a neural network. And it's the same as QTable method, the environment, so it's identical, so I'm not gonna go over again. We initialize the neural network parameters. Initially, we have 16 input, and then in the middle, we have 3 layers of 50 nodes, and the output should be 4 nodes, indicating the 4 action choices Q values. Okay. So we have 16 states, 4 action choices, and a Q value of NS and NA. The gamma time discount is 99%. We have epsilon grady, and we run 300 episodes. Okay. So how do we build a network? Very easy. From the input dimension, go to the 15 nodes here, and then have an output node of 4 nodes. In the middle, we have leaky value. It's like a ReLU, but a little bit better convergence. I didn't use the dropout. You could, batch normalization and all that. I didn't. You don't need them. Then we compile the model, and this is our DQN, deep Q network. Let's declare and build this network, build Q network. And then here's how to run it. And it's pretty much similar like the QTable method. Except to get the Q value, now you need to run the DQ network. So the DQ network, DQN, predict based on the one-hot coding. So NP identity 16S, S plus 1, it basically puts a 1 in tile S, isn't it? So this is what we do. And it makes a prediction of the Q all. So here, one-hot coding, the input, for example, is S0, then 1, and then the rest of them 0, and so forth. So this is what's getting, and then it spits out the Q value, the 4 numbers. Among the 4 numbers, pick the largest, and that's the action choice. But once in a while, with probability 0.1, so 10% of the time, we'll do something else, which is pick a random number, and if that is here, if it's less than 10%, then Amax, put the A equal Amax. While if A equal A max, if it's the same, then basically put a different random integer. What it does is that with 10% of the time, we'll choose an action choice that is not the largest Q value. And this is because sometimes the program may get stuck into a local optimum and stay there. We want to once in a while with small probability deviate from that choice, just in case. Okay, so now we have the state and the action chosen. You will get the next state reward and whether you died or not. The maximum Q1 So you put all the target Q, the 4 Q values, you copy from the old value, but the one that you chose the action there, you basically replace it with the reward plus time discounting on the maximum Q1. So that is how you get. So the target Q will then do a supervised learning where everything is matched, so there's no error generated, but here will be an error generated and the weights will be adjusted accordingly. Okay? And then you update the R and the S1 and then keep playing it. Okay, so you can keep doing it. So that will run, and it's gonna run for a while. So let's come back when it's done. Okay, it's done running. Sometimes depending on the initial value, it may not give a satisfactory result. Just click it again and run it again. You'll get it. Okay. So how many times it was correct? Total number of episodes and how many episodes were successful? 77%, not bad. And for example, if your position, you have like here, position, the Q value is at tile 0, 9, 4, 9, 8, 7, 7. So left down is the correct move here, they suggest. Down is actually a good move, isn't it? Yeah. So you can see that the program actually did learn fairly well. So, and you can test the actions of the desirable actions, 0, 1, 2, 0, 1, 2, 3. So down is the move, and then tile 5. So 0, 1, 2, 0, 1, 2, 3, 4. So tile 5 again. Down is a correct move. Okay, so you can see that it did fine. Okay. So this was how to show a deep Q network for reinforcement learning of the fraud. Thank you for watching this episode.